Hello friends, in today's class we are going to talk about arithmetic simplification, strength reduction and constant folding. Okay, so the next set of optimization is a peephole optimization, and these optimizations are generally largely considered as machine dependent optimization. Okay, so a statement by statement code generation strategy often produces target code that contain redundant instruction and suboptimal construct. The quality of such target code can be improved by by applying optimizing transformation to the target program. Okay. Now, a simple but effective technique for locally improving the target code is called peephole optimization, a method for trying to improve the performance of the target program by examining short sequence of target instruction called the peephole. Okay, so we will be just examining what the short sequence of target instruction. Now, and that is called peephole, by replacing this instruction by the shorter and faster sequence whenever possible. Okay, so that is the idea of peephole, that first of all, target code we will trying to improve, and in the target code we will see the small set of sequence that is that we can replace. So in this we have a redundant instruction elimination, flow of control optimization, algebraic simplification and use of machine idioms. Okay, so that is the four different categories of the peephole optimization technique that we are going to see. So let's see the basic example for them. That redundant instruction elimination is that if you see the instruction sequence of load and store, that a value will be loaded into register R0. So R0 will be loaded with the value A, and this is a load instruction, and this is a store instruction which is loading the R0 value back to A. Okay, now to do so there is no point of loading and storing the same value to this register R0. Okay, so there is no use of, let's say, loading and storing same value to register R0. If it is the case, we can remove this set of statements, and that is called redundant instruction elimination. This is one example of redundant instruction elimination. The next is your flow of control optimization, and in flow of control optimization is very simple, that if you have a go to L1 is the label, and again in that label we have a go to L2. Okay, so now we are jumping here, like here L1, go to L1, and L1 is the label which says that go to L2, and suppose this is L2. So we are coming from here to here and here to here, and optimization technique says that I can directly come back here to here. So rather than writing this, we can replace this sequence by go to L2, and here we will not change anything. Okay, so directly we can transform it to go to L2, and L1 will be its own sequence that will say that go to L2. So that is the flow of control optimization. The next one is your algebraic simplification, and in algebraic simplification that we have already seen this algebraic simplification, that x plus 0 and 0 plus x is equal to x, x multiplied by 1 multiplied by x is equal to x. There is no point of subtracting 0 from the x, there is no point of dividing x by 1. Okay, so this is called algebraic simplification, and in algebraic simplification we have one more part, that is a reduction in the strength, that we have also seen, and x square will be replaced by lower cost or cheaper cost operation, that is multiplication. Division can be replaced by lower cost or cheaper operation, that is multiplication. Okay, so that term is called algebraic simplification. The last one is your using of machine idioms, and there's some statement is given here. The target machine may have a hardware instruction to implement certain specific operation efficiently. Okay, so we may have some hardware provision to implement certain instruction efficiently. Detecting situation that permit the use of this instruction can reduce the execution time significantly. So now it totally depends on how my hardware has been written. Hardware has been written. Hardware is supporting or not. So not written, constructed. Hardware is supporting that category of instruction. Okay, so if it is there, then it will definitely use if you use that instruction, it will definitely improve the performance. For example, some machine have auto increment and auto decrement addressing mode. Okay, so even if you're doing x equal to x plus 1, okay, now this is addition, but if we do this thing by using in some situation, if there is a for loop, and if we can just have this auto increment and auto decrement mode, then the entire efficiency of the code can be improved. These add or subtract one from the operand before or after using its value. The use of this mode greatly improve the quality of the code when pushing and popping a stack. Okay, so in that case, if you're doing pushing and pump, then this codes becomes very useful. As in the parameter passing. Now this mode can also be used in code for a statement x equal to x plus I. So if you're doing the amount of the increment, then also this code can be used. Sorry, not I, x plus 1. Sorry, x equal to x plus 1. Also it can be used. So the overall idea means I have read many things over here. Means I believe some of them make sense, and the only thing it says that if we have a hardware support available for certain category of the instruction, okay, their hardware support, then we just use those instructions and can greatly improve the performance. Okay, so that is the idea. Okay, so that's all for this peephole optimization. I hope I'm clear over here. Okay, thank you.